Okay, gentlemen, so due to extended weather issues, I'm going to make a video and hopefully we can learn something despite not being in person. So what we've been doing, which you may or may not remember, is covalent bonding in Lewis structures. We were showing where all the electrons were when covalent bonding or sharing electrons between nonmetals happens, and we were graphing out those connections, drawing out those connections. So I got 4 examples here, and I'm going to do them, and then we're going to move on to what is called molecular geometry, which just takes this Lewis structure that we're going to learn and predicts what shape it'll be in 3-dimensional space. So if I have carbon tetrahydride, which is also known as methane, it's natural gas. Carbon has 4 valence electrons, wants to make 4 bonds, and each hydrogen has 1 valence electron and wants to make 1 bond, and they want to make that number of bonds to be like the nearest noble gas with their valence shell. So carbon and pretty much everything wants to have 8 valence electrons, except for that first energy level, which is hydrogen and helium, which are happy with 2. The way they gain electrons, even though both of them want to gain and neither of them want to give up, is by sharing. So they share pairs of electrons. Each one puts 1 into the electron. So carbon put that one in, hydrogen put that one in, and they both get to count each of them. So the carbon has 2, 4, 6, 8, and each hydrogen has 2 in their valence shell, which is what they want. And you end up with a final Lewis structure that looks like this. We just replace the bonding electrons with dashes. So that is the final Lewis structure for methane or carbon tetrahydride. I'll move these down a bit. Let's find some more space here. So I'll do CO2 next. We've already done carbon's electron dot structure. 4 electrons, wants to get 4 more. Oxygen has 6 and wants to gain 2 more. So carbon wants to make 4 bonds. Oxygen wants to make 2 bonds. And so 2 oxygens and a carbon work out pretty well because an oxygen comes up, makes its 2 bonds with carbon. The oxygen is happy. It's going to stop bonding now because it already has 8. And the carbon still wants to make 2 more bonds, so it just finds another oxygen. It makes those bonds, and everything's happy. So the carbon has 1, 2, 3, 4, 5, 6, 7, 8. And each oxygen has 1, 2, 3, 4, 5, 6, 7, 8, which is what they want. And again, when we draw the Lewis structure, we just show the bonds as dashes. So each dash is 2 electrons, and those electrons count towards both connected things. And we still show the 4 electrons that aren't bonded on the oxygens in this case. If their electrons don't go into bonds, you still have to show them. Methane didn't have any unbonded electrons, so we didn't have to show those. So moving on to water. I'll move these down a little bit more. That was not what I wanted to do. Down a little bit more. Water, hydrogen and oxygen. So we've seen both of those. Hydrogen has the 1 electron, wants to make 1 bond. So oxygen has 6 electrons, wants to make 2 bonds. And again, hydrogen with 1 electron wants to make 1 bond. So the hydrogen makes a bond with oxygen. The hydrogen is now completed, so it's done. So oxygen still wants to find 1 more electron, so it needs to make another bond, so it finds another hydrogen. We draw that Lewis structure. We've got oxygen with its 4 valence electrons that aren't bonded, and then we show the bonds as dashes. And if we look, the oxygen has 1, 2, 3, 4. That counts as 2, 5, 6, 7, 8, so it's happy. Each hydrogen has 2, so they're happy. Finally, we're going to do nitrogen trihydride, which is also known as ammonia. Nitrogen starts with 5 valence electrons, wants to gain 3 to get to 8, so it wants to make 3 bonds. 1, 2, 3, 4, 5. Hydrogens, we've done a bunch of, just want that 1 bond, so hydrogen, 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 and oops, forgot that dot there. There we go. And so hydrogens each want to make 1 bond, nitrogen wants to make 3, so you get 3 hydrogens bonded to it, and everything gets where it needs to be. 2, 4, 6, 7, 8 for the nitrogen. Each hydrogen has 2. And the final Lewis structure for that would look like this. Again, you still have to show those valence electrons. So we're going to talk about next, same view here. We're going to talk about next is how we use that to predict shapes. And the theory we use for that, and you should have gone over this in that online tutorial, is called valence shell electron pair repulsion, often kind of initialized as VSEPR. I know it's VSEPR, but people say VSEPR. That's what I'm going to say. That's what the community says, so you kind of got to get used to this. And basically what this says is that for simple molecules, so molecules, by simple molecules, we mean molecules that have one central atom, and everything else is just bonded to it. And so if I go back, these guys here would all be simple molecules. Those would be the Lewis structures for simple molecules. So I can bring them over. So these are all simple molecules. One central atom, things connected to them, all simple molecules. We can predict the shapes of these, the three-dimensional shapes, because electrons are all repulsive. Bonds are made out of electrons. The outside of the bonded atoms are electrons. So basically the bonds and unbonded electrons try to stay as far apart from each other as possible. And we can predict what that is. We can predict the farthest, say, 4 things can stay apart in three-dimensional space, or 2 things, as these two have. So we can predict how far apart they can stay. And I'm going to have you guys using for the homework this simulation, which is a PhET simulation, it's linked. But let's just think about what the carbon tetrahydride, that first one. It was just one carbon with 4 single bonds connected to it. Well, there's one single bond, and of course we can move these anywhere. And that's just one single bond, so it doesn't really matter. That's going to be linear because between any 2 points is a line, or you can draw a line. If we put a second bond in there, the bonds stay as far apart as possible. Even if I drag them around, they'll always go back and stay as far apart as possible. And for 2 things, that's going to be 180 degrees, right? If I try to bring them any further apart in one direction, they get closer in the other, so they adjust. 180 degrees is as far apart as they can stay. And the reason they do this is that bond is made of electrons, which are negative, and that bond is made of electrons, which are negative. So if we keep going, adding 3, 4, which is what carbon tetrahydride is, the shape we get is called a tetrahedral shape, or a tetrahedron. We're particularly interested in this molecular geometry. I'll talk about the electron geometry in a bit. But molecular geometry is the tetrahedron. That's 109.5 degrees apart. Now you might think, why isn't it 90? And that's because you have 3-dimensional space. For 2 bonds, which is 180, and 3 bonds, everything stays in the same plane because that is in fact as far apart as they can stay. So you got 180 degrees for 2 bonds. That's, a circle split 2 ways. You got 120 degrees for 3 bonds. So you maybe think 90 degrees for 4 bonds, but they no longer stay in the same plane, and by adjusting into 3-dimensional space, they can get 105.9 degrees. You do not have to memorize the bond angles or these names. For the testing quiz, you will be given a sheet that has all this information, or at least the information you'll need. So all of these bonds here, they all repel each other because they're all negative. They have to stay connected to the central atom because they're chemical bonds. There's an energy advantage to staying connected. But within that restraint, they all stay as far apart as possible. And that's where we get the shapes. The valent shell electrons, these electrons that are making bonds, all repel each other. And because of that, you can predict the shape. So if we were to go back here and look at the shape, so the molecular shape, which is also called the molecular geometry. If I wanted to draw that out, I'd put my carbon in the middle, and I'm going to draw it with a ball and stick model, which is fairly common, and my hydrogens on out to the sides with bonds showing. Now this was tetrahedron. It kind of looks like this. I know my drawings aren't great. I wouldn't expect your drawings to be, well, I'd probably expect your drawings to be better than mine, but I won't hold you to that standard because it's not hard. But there is 109.5 degrees between each of these. So that's how we represent the shape. And I would also have you guys write the shape, tetrahedral. It's a tetrahedron. A tetrahedron is a pyramid that has a triangle base, or a 4-sided die, if you would prefer that. That's why tetra, because tetra means 4. It's a 4-sided cylindrical or four-sided geometric solid. You don't have to learn any more geometry than that, though. So if we go to CO2, CO2 has two things bonded to the central atom and nothing else going on there. So it's pretty easy to predict what's going to happen, but I just want to make sure we understand that double bonds don't really change this situation. So if I remove everything and we do a double bond and another double bond, the double bonds, they can't split apart. They still have to be between the oxygens and the carbon in the middle. Uh, so the two bonds that are between this one have to stay here, and these two bonds have to stay together. But within that, they will stay as far away from each other as possible. Because again, electrons repel other electrons. So it's just two things, 180 degrees, linear. That's it. The molecular geometry is linear. So nothing complicated about it. Uh, Carbon, and then got your oxygen and your oxygen. And we would just call that linear. Terrible A, but we'll survive. So that's linear. Now, this is where it gets a little bit more tricky and where you have to really be careful about these electrons, drawing these electrons that aren't bonding electrons. You have to make sure they're still there. Because if we look at water, dihydrogen monoxide, technically, I guess, what you would think maybe is, oh, it's linear. It's got two bonds. They want to stay as far apart as possible. And that is true, but it also has these other unbonded electrons. There's these other negative areas because electrons are all negative. It doesn't matter whether they're in a bond or not. So these are going to affect the shape. So if we go back and we map out water, I'm going to here clear everything. We'll put in the two bonds. And yes, if it was just the two bonds, that would in fact be linear. But it doesn't just have two bonds. It has two unshared electron pairs. In other words, two pairs of electrons that aren't in bonds. And so if we put them in, they also repel stuff. They change the shape. They repel as well, and you'll end up with a shape that has 109.5 degree angles. So you see 109.5 degree angles there, because these electrons also push down on the bond. So they take the shape that is most helpful for that. Now, when we talk about the shape of the molecule, the electrons, because they're tiny, even though they affect the shape, they aren't part of the shape. So the shape is just this bent or V shape. So the shape would be bent or V shape, but the electron geometry, which includes the electrons, we don't usually talk about that one, is tetrahedral. It has a tetrahedral electron geometry. If you look at this, it's that 109.5 degree angle with the four things sticking out. But we aren't usually as concerned about that. We're concerned about where the actual atoms are in the molecule. So we're concerned about this bent geometry. So if I were to look at that one and draw the Lewis structure, it would look like this, with oxygen in the middle, and then your two hydrogens on the outside, and then we show the four dots around that central atom. Now, you might notice, oh, carbon dioxide also has dots, extra electrons around it. They aren't on the middle atom, so we don't really care about them because this is all one big negative area, and it doesn't matter if it has more extra electrons on it because that just makes it more negative. Still going to repel. These two things are still going to repel each other. These electrons can't leave this oxygen. So we only care about free electrons on the central atom as far as the shape is concerned. You still need to draw them there for the Lewis structure, but as far as the shape is concerned, we only care about them on the central atom. So last one is ammonia, which is nitrogen trihydride, and we got three bonds and one unpaired electron, one unshared electron pair. That's the words. So we'll plug that into this thing. So clear everything. Three bonds. Well, yeah, three bonds is going to be what we call trigonal planar. It's a triangle in one plane, 120 degrees. But that's not all there is. There's also one pair of electrons that aren't shared. So that changes the shape. It kind of pushes everything, pushes all those parts of the triangle down. And you end up with this shape called trigonal pyramidal, which is just a triangle-based pyramid. And that's all it is. The electron geometry, which if you include the electrons, is in fact tetrahedral. This has that kind of basic tetrahedral shape. But if we don't include them, it just looks like a pyramid that is in fact triangle-based, so trigonal pyramidal. And that is the shape of ammonia. So ammonia, nitrogen in the middle, and then 3 hydrogens. And again, do your best drawing these. They're not incredibly hard to draw, but do your best, and you show the 2 electrons on there. Uh, Showing the electrons in ball and stick models is optional, but I like to because it shows you why they're the shape they are. I think it is helpful, and it brings over all the information from the Lewis structure over. So the idea, again, the basic idea with VSEPR is that everything that is bonded to that central atom stays as far apart as possible. And that includes unbonded electron pairs. They also affect the shape. Bonds and electron pairs together are all called electron groups because each bond has some electrons in it and the unpaired electrons have some electrons in it. So you see the term electron group, which may show up on the work. It's just how many things are on the central atom that repel each other. So this would have 1, 2, 3, 4. 4 things on the central atom, 4 electron groups. If we clear everything, we do 2 double bonds. This is just 2 electron groups. That's 1 group, that's 2 groups repelling each other. But if I added that, that would be 3 groups. 1, 2, 3. Now, this isn't a shape that's going to work with this number of bonds and lone pairs, but that doesn't matter. These would be all bonds, whether they're single, double, or triple, and lone pairs all count as electron groups. And we only care about the number of electron groups on that central atom because those are the ones that affect the shape. So that is a relatively quick introduction to VSEPR and molecular geometry and a bit of a review of Lewis structures. This is what you're going to be doing on the worksheet. I suggest you use that PhET simulator, the one I was showing, with the nice animation as you change it to figure this stuff out. And then we'll go through it whenever we see each other, whatever class. I think Wednesday we may have school, so we'll see. Have a good day. Enjoy your days off. See you guys when we see you.